This lecture has covered the chi-square test and the F distribution. So our main objective is to use a contingency table to find the expected frequencies. Also use a chi-square distribution to test whether two variables are independent. We call this the chi-square independence test. Again, chi-square is a non-parametric test, and we normally use the nominal data variable. So we start with the contingency table. So normally a table consists of rows and columns. We are assuming R here means rows and C means column. And that will be the size of the table. Same concept as a matrix. The size of a matrix in mathematics is the number of rows by the number of columns. So here we say R by C contingency table. Again, R represent the rows and C represent the columns. This will show the observed frequency for the two variables. So we may have one variable on the columns and one variable on the row. Again, we will see an example soon. Also, the observed frequencies are arranged in R rows and C columns, as we said earlier. Also, the intersection of a row and a column is called a cell. So this is an example. So here we have two variables, age and also company size. And we have 1, 2, 3, 4, 5. So this will be 2 by 5 table, the size of the table. We have two columns, two rows, which is small, mid-size, one row, and the large, and second row. And that's again the company size. And the ages or the age of different CEO for each company. So here I would say by looking at this table, we want to find out if the CEO age related to the size of the companies that is the CEO. So here we say the contingency table shows the result of a random sample of a 550 company CEOs classified by age and also the size of the company. So if we add all the values here, it should be 550 CEOs. So for example here, the small, mid-size CEOs under the age of 40, we have 42 for small, mid-size, and only 5 for large. So finding the expected frequency, here we are, first of all, we should assume that the two variables are independent. In this case, we have the size of a company and also the age. And also you can use the contingency table to find the expected frequency for each cell. So to find the expected frequency for each cell, we use the formula, the sum of row R times the sum of column C divided by the sample size. So for example, in our example previous table, the number of CEOs are 550, so that will be the sample size. Now the R will be the row and the column. So if I'm in the first row and the first column, then I'll say Y11. Second row and third column, Y23. So the first value should be the row position, and the second value should be the column position. And that's what we call the cell, the intersection of the row and again, the column. So again, that's the formula. Again, expected frequency, RC, is the sum of row, whatever the row is, first row or second row, times the sum of column, whether first row or first column, second column, third column, divided by the whole sample size. Again, we're going to see example here. So the same data we have previously, the company size, small and mid-size, first row, the second row is large, and we have the ages from 39 till 70 and over. And we have age, category of age. So here first of all, since we want to find the expected frequency, most important, we need a total. So here we can see that we included the total for the first column, second, third, fourth, for all the columns. And also we have the total for all the rows. The first row is 300, second row is 250. So with this, very straightforward. If I want to find the expected frequency, let's say Y11, the first row and the first column, then it will be the sum of what? The first row and the first column. So it will be 47 times 300 divided by the total, which will be 550. Again, I think we have example. Let's keep going now. So that's the example E11. It will be the total row is 300 times the total column is 47 divided by 550. So this means the expected frequency for the first cell, E11, is 25.64. So the same process we have to use for the rest. E12 will be the first row, second column. So first row is 300, second column is 87, the totals. So we have 300 times 87 over 550, which gives us 47.45. The same thing, we can go to E13, the first row again, 300 total. The column total is 193, so it's 300 times 193 divided by 550. Then we keep going. The next E13, that is the third column. We have 180 for the total third column, and the same amount for the first row, total 300, divided by the sample total size, 550. And the last one we have for the first row, we have 43 for the column times 300 over 550. And we have to do the same thing for the second row. So we have to look for E21, E22, E23, 24, 25. And that's what we have here. E21, it will be, so now the second row total is 250. So now we are going to use 250 throughout. 250 times 47 divided by 550. 250 times 87 divided by 550. Then 250 times 193, which will be between 50 to 59. The column is 193 divided by 550. Then 250 again divided by, times 180 divided by 550. Then 250 again times 43 divided by 550. So this is how we find the expected frequency. Now, the next, we are going to use the expected frequency to test our variable. In this case, let's say chi-square dependent test. The goal is that we want to test if the two variables are independent, or if we say we are independent, if we say the company size and age, these two variables are independent, again, we mean that age doesn't have anything to do with company size. It doesn't affect company size, doesn't affect the age of the CEO. And that's what we're going to do next. So we can see the process is more or less hypothesis testing. Hypothesis testing. First, we collect our sample. We have our sample already. We were able to find what the expected frequency for each category. Again, chi-square is based on counting frequency, expected frequency. So if we find the expected frequency finished, now we can move on to next step and use it to find out if there's any relationship or the two variables are independent. So chi-square dependent test, we use it to test the independence of two variables. Also, we can determine whether the occurrence of one variable affects the probability of occurrence of the other variable, which again is the whole concept of chi-square dependent test. So for chi-square dependent test to be used, the following must be true. First, the observed frequencies must be obtained by using random sample. So, and most hypothesis tests always we get our data through random sample. Also, each expected frequency must be greater than or equal to 5. So we can look at our data here. We can see if we can be able, first of all, we know already it's random sampling. Yeah, so all of them, we have 5, at least 5 or more. So if we should have less than 5 for the expected frequency, which we have 21, 39, 87, etc. And then we go the other way, we have 47, 98, 105, 2, 3, 4. So if all the values are greater, at least 5 or more, which we said here, if each expected frequency must be greater than or equal to 5. again, the expected frequency, not the sample size. For example, let's say the CEO between the age of 39 to, let's say, 50, we have only 2. That is the data. That's not the expected frequency. The expected frequency is what we calculated using, again, the row sum times the column sum over the total sample. Okay, so we meet the condition. If this condition is satisfied, then the sampling distribution for the chi-square dependent test is approximated by chi-square distribution with the following formula: R minus 1 times C minus 1 degrees of freedom, where again, as we said, R and C are the number of rows and columns, respectively. Now, if these conditions are satisfied, then the sampling distribution for the chi-square dependent test, as we said, approximated as the following. And also the test statistics, we use the formula here, x squared equal to the sum, the difference between the observed and expected, all squared divided by the expected frequency. So again, the O represent the observed frequency, and again, the E represent the expected frequency. Observed frequency will be given to us. That's more or less the sample. And the expected is what we find. So the test is always a right-tail test for chi-square independent test. So now let's go through the steps of testing or finding using the chi-square dependent test. And that's the goal of this lecture. So first, we identify the cream. We state our HO and HA. Then we specify the level of significance. That's identify the alpha. And also we identify the degree of freedom. Very important. We are going to use it for the table. So degree of freedom formula for the chi-square dependent test is R minus 1 times C minus 1. R and C again are the number of rows and columns in the contingency table. Then we are going to determine the critical value using the table table 6 in our textbook. Again, depends on what textbook you are using, but this textbook is for finding the chi-square, the critical value. But the textbook we are using in this course is table 6 in appendix B. What I mean by the table is that some textbook may have the chi-square critical value to find, and the table maybe to be in appendix A, or it to be table 4, table 1, it depends. So next we determine when we know that, again, we have the level of the alpha value will be given to us, and also we know the critical value, so we can determine the rejection region. Then there we find the test statistics. Now we say we can make a decision to either reject or fail to reject the null hypothesis based on what the test statistics, whether the value will be in the rejection area or not rejection area. So the chi-square is in the rejection region, we reject HO, otherwise we fail to reject HO. Then we interpret the decision in the context of the original claim. So we are going to use the same example. Now we already have our observed frequency, as we said earlier. The observed frequency is the data that we call the sample that we collected. So 42, 69, 108, these are the number when we collect the sample. These are the number of CEOs based on their age and the company size. Then we can remember, we find the expected frequency using the formula, the sum of the row times the sum of the column divided by the total, again, sample. So now we are good to go. We can find the test statistics now because we know the O and also we know the E, observed and also expected frequency. So let's state our HO and HA. CEO ages are independent of company size. No relationship between those variables. Or they are dependent, which means there's a relationship or association. Alpha is given to us to be 0.01, and we were able to find the degree of freedom based on the contingency table, the data set. We have category of number of ages and number of company sizes. Number of company sizes is only 2. For example, we may have 3, let's say small, medium, and large. but small and medium are together as one, and large is one. So rows are two. We saw the column is five different categories of ages of the CEO. So we're able to find a degree of freedom. Now, with that, we can be able to come up with a critical value. And here, again, the alpha is 0.0. Remember, we say always the test is a right tail test. So we have our value 0.01, and also critical value is 13.277. Now we need to find the test statistics. Again, the critical value, we find it from the table, the chi-square critical value table. So now we are going to find the chi-square value, the test statistics. So we have to, now we have different categories. So we start with the first, what we have here, let's go to the table, is what we had. So we are doing each category for each table. So we should have 10. I think it's 1, 2, 3, 4, 5, and age, company is 2. So we should have 10. Then we have to sum all together. Remember the formula summation. We sum all the value. So we have the first one, second, 3, 4, 5, 6, 7, 8, 9, 10. And that's the formula. The observed value is at the top, which was 42. The expected frequency we find 25.64 all square divided by expected frequency. So we use the same formula for each table, each cell in the table. Again, one more time to make sure we understood, I'll go back to the table. So this is the table. To find the chi-square here, to be the value here, it can be 42 minus 25.64 or 25.64 minus 42. It's the same because we are going to square it. So if the answer is negative, when we square is positive. If the answer is positive, when we square is positive. So the difference of 42 and 25.64 divided by the expected is 25.64. Then the difference in the second column, first row, the difference of 69, 47.45 all square divided by expected, which is 47.45. And we keep going. So that was, we have 10 cells, so we have 10 values here. Now, when we finish, we had all of, so we can see we are adding all the 10 values, and that gave us 77.9. So now we are going to look. We have the critical value and the test statistics. So we can see where the 77.9 is. So we come to the conclusion that we are going to reject HO because it's in the blue area. Now, always the brown area is to accept the HO. So here we will say in general, based on here, we can say that if the test statistics value is greater than what? The critical value. So we are going to reject HO. So here we say there's enough evidence to conclude that the CEO ages are dependent. So there's association between the two. They are dependent on the company size. So there's a relationship between the CEO ages and the company size. So in these lectures, we learn how to use a contingency table to find expected frequencies. Also, we use the chi-square distribution to test whether two variables are independent. Now, in order to use, as we said, the independent test here, we always have to find the expected frequency. Observed frequency will always be the data that we collect, the sample data we collect. So again, wish everybody the best and see you in the next lectures.